So let me just give you a 5 short tricks or formula of calculating any question on what? On half-life. Let me call it what? Tricks of half what? Half-life calculate questions. The first one is we all know that what? The half-life, the first formula is half what? Half-life T is the radioactive time over N. This will be what? Half-life equal to the what? T over what? Over N. Call it equation what? Equation 1. We derive it from definition of half-life. This N can also be in form of this. If you could still remember now, I did it here. N equal to what? T over what? Over this. Abi? And the next one is what? Disintegration what? Ratio. The second one, I can say what? Disintegration ratio, to call it what? R. This disintegration ratio is the ratio of initial value of what? Of atom. Is the ratio of what? Initial what? Initial value of what? Atom to the final value of atom remain. This one is called N0. Here we call it what? Ordinary N. Therefore, my disintegration ratio R is equal to the what? N over what? N what? N, sorry, N naught over what? Over N. If I call this one equation 1, this will be what? Equation 2. And the second one is what? Disintegration what? Ratio. How? I can relate it to the what? To the N. Let me say what? The third one is disintegration ratio R related to what? To N. If I relate the disintegration ratio R to what? To N, it will be give us what? R into 2 exponential N. And we all know that what? Our R is what? Is this. We can also have it in what? N naught over N 2 exponential N. And don't forget that what? This N here is the same thing as what? Where what? Where N is half-life over T. You can also put it what? There. So this, you can have T this, N equal to the what? 2 into what? Half-life over T. Call this one equation what? 3 for me. Then from the law of what? Of logarithm. From law of what? Logarithm, that will be next case. From Law of logarithm. You can say what if r is 2 exponential what? Mm-mm. And yeah, will be small t over t, sorry, small t over capital letter T, which is half life. Yes, 2 exponential what? N or small t over what? Over t. If r is what? Is this from law of logarithm. By taking the logarithm of what? Of both from the law of logarithm, we will have what? T over capital letter T is equal to the what? Logarithm of r base 2. Take logarithm of what? Of this law of logarithm. This, go to this, we have this. If you take it back, it will give us what? This. By applying that, you can finally arrive to, if we say we have capital letter T here is equal to small letter t over what? Logarithm of what? R, the integration ratio to base what? Base 2. This will be the what? Equation what? Equation 4. And the last one is what? Fraction. Fraction of initial atom. Initial what? Atom or mass. Initial atom remaining. Or mass what? Remaining. Initial atom remaining on decay. Yes, initial atom remaining on what? On the what? Decay. I'll call it what? FD. Hmm? So is the reciprocal of disintegration what? Ratio R. Hmm? Or I put it this way. Or you can say what? Initial atom what? Remaining FR is equal to the what? Final number of atom remain over initial number of atom present. Which is written as what? FR is what? Number final over what? Not. But where what? Where R is N naught over what? N. The integration ratio. But I said it's the reciprocal. Abi? So if this is this, then what happened to the what? 1 over R. 1 over R will be what? N over N what? N naught. That will be the what? 1 over R. Therefore, the fraction of atom remaining FR will be 1 over what? The integration what? Ratio. Call it equation what? Equation 5. So This equation 5 plus what we have here from 1 to what to 10. Combine it together, making what 15. You can use to solve any question on radio what activities. Let's solve questions now. I will write like 10 questions on board. We apply the question to what to solve it. Hey, sorry, lest I forget, before we rub it up and solve numerical problem on half-life, let me add this, please. We have what we call what average life. Average what life or mean life. Yes, of radioactive what elements. This is the what ratio of ratio of what total lifetime of all the atom. Total what lifetime of all the atom and total number of atom present and total number of atom present initially in the sample. So the formula for the mean life is the reciprocal of decay constant. But the relationship between what the average life and the half-life is the average life symbol is this. With half-life, it be 1.44 times what? Half-life. This is the relationship between what? The average life and what? An half-life. So yeah, let's solve question on this now. Solution. Let's solve all these questions. 1 to 11. Look at question number 1. An iodide 131 has half-life of 80 days. Calculate the what? Calculate the decay constant. So 1, we are given the iodide 131 as a mass number, as atomic number, and it has a half-life of what? 850 days. Calculate decay what? Constant. So the half-life given there T for the iodide is what? 8.05 days. We need to convert it to what? To seconds. By converting it to what? Seconds, what we do? This in seconds will be what? Half-life of 8.05 days. How many hours do we have in a day? Is what? 24 what? Hours. Multiply the what? 3,600 seconds. So this it will be in what? In seconds. By pressing the calculator of this, it's like it will going to give us what? Half-life of what? 6.95 times 10 raised to power minus 5 seconds. This is what? The half-life, but we are asked to find the what? Decay constant, which is lambda. Which formula relates decay constant and half-life together? You check it now. We know that what? Using this decay constant will be equal to the what? 0.693 over what? Half-life. So decay constant will be what? 0.693 over what is what? The half-life is half-life there given is what? 6.95 times 10 raised to power minus 5 By pressing the calculator, the final answer here will be what? 9 times what? The final answer here will be 9.97 times 10 raised to power minus 7 meter. So this is what? Decay what? Decay constant. Check the question number 2. The half-life of tritium is 12.33 years. Question 2. The half-life of tritium is what? 12.33 years. What is the number of tritium nuclei that we have the activity of this? Yes. The number of tritium nuclei we are looking for, we are given the what? The activity of. From this question, we have our what? Activity A should be what? 3.70 times 10 raised to the power 10 per seconds. That's activity. But we are looking for the what? The number of nucleus, which is what? N, number of nucleus. And here too, our wave lambda here is also what? Unknown. Wavelength. Let us find the wavelength by using what? Using the half-life of lambda is equal to the what? 0.693 over what? Over half what? Half-life to know the what? Lambda. By applying this, we have 0.693 over what is half-life? 1233 multiplied by 24. The way we convert this to seconds, 24 times what? 3660. So if you press your calculator together and press it, it's supposed to give you what? The final answer for lambda will be 1.382 times 10 raised to the power minus 9 per seconds. That's what? Formula for lambda. And the next thing is what? To know the what? The number of nuclei from the what activities. The activities of an element are what? Activity of element or nucleus of an element is the product of lambda with and what? An n. And we are looking for this n. The number of nucleus of tritium will be what? Are what? Activity of elements over what? Lambda. So what is activities given? We are given 3.70 times 10 raised to the power 10. Everything over what? What is the lambda we calculated here? 1.382 times 10 raised to the power minus what? 9. So if you press the calculator very well, we have what? Lambda here is 1.7. This is 1.7. Yes, 1.7. Press the calculator very well. Our n will be what? 2.08 nuclei. That is what? The answer for question number 2. Let's check for question number what? Number 3. The half-life of AT215 is 100 microseconds. So we are given that what? The half-life here is what? 100. So number 3, our half-life given as what? 100 microseconds. Yes. The time taken for the radioactive element of the sample to decay to the 1 of the 16th of initial value. We are looking for what? Small what? Small t here. Abi? Like this question is also what? Very straightforward. Forward. Using n over what? N naught equal to what? 1 over 2 into small t over capital T. So this 1 n over n is the fraction given. We are given that what? This is equal to the what? 1 over what? This of what? Initial what? Initial value. So that is what? The n to the n naught is 1 over what? 16. So we can now put it here. We have 1 over what? 16 equal to what? 1 over 2 into what? Small t over 1 what? 100. So if we apply the what? Law of indices, this expression can also give you what? 1 over 2 into bracket what? 4. So that will give us 16. And we have what? 1 over what? 2 into bracket what? T over what? 100. This we cancel this out. We have 4 into what? T into 1 what? 100. Cross multiply. Our T equal to what? 400 microseconds. That's the answer for what? Question number what? Number 3. The next one is what? Question number 4. So let me rub this solution to number 1 here. So the next question is question number what? 4. We are having 4. We are given a radioactive substance has the half-life of 20 hours. What is the fraction of original radioactive nuclei will remain after 8 what? 80 hours. Yes. Half-life is 20. Small t is what? Is 80. So whenever you are asked to find the words, what is the fraction? Fractional remain. So here you observe that what you are given what? This capital T should be a what? 80. Half-life is what? 20 is 80 seconds. And the half-life is what? Is 20 what? Seconds. You are now asked to find the what? The fraction of original what? The active element. If they ask for any time they ask for fraction, it's F what? R. Whenever they ask for the fraction what to remain, apply this sort trick. The fraction remain using for any radioactive element. This is the formula. I said you use what? FR should be reciprocal of what? Of R. Distribution what? Ratio. And this R, we know that what? Or F is equal to the what? This R is 1 over what? 2 small t over what? Capital letter T. If you check the what? The formula I gave you, you have it like this there. The fraction what? Remain. So since the fraction remain here, it will be what? F what? R should be 1 over 2. What is my small t? 80, capital T, 20. So it will now give you what? 1 over what? 2 in here, 4. 2 goes to power 4. Therefore, the fraction remain is what? 1 over what? 16. That will be the what? The final answer for that one. Whenever you are asked to find the what? The fraction remain, apply this short method. The fraction remain is equal to the what? Reciprocal of R, where R is what? 2 exponential small t. R is what? 2 exponential small t, capital T. Capital T is what? Half-life. If you look at what the question number 5 is almost the same with what? Question number 4. We are given the active material has the half-life of 35 days. Calculate the fraction of the mean if the original protein is what? 100 what? 105 what? Days. Let's check it now. It's what? It's the same with what? What we apply or we did for question what? 5. If you look at 5 now, we have a radioactive sample of material has a half-life of 35 days. Capital letter T is what? 35 days. What is small letter t? We are given as what? 105 days. What is the fractional mean? The fractional mean for radioactivity is what? Reciprocal of what? Of R. Abi? Where R is this, or you can say what? Fractional mean is what? 1/2 to the T over capital letter what? Small letter T. So by applying this formula now, we are going to edit with what? Fractional mean should be what? 1/2. What is this? We have what? 105 over 35. So 35 105, we have 3. We now have what? 1 over what? 2 raised to the power 3. So the fractional mean will be what? 1 over what? Over 8. So the fractional mean is 1 over what? 8. Anywhere you're asked to find the fractional mean, don't forget to what? To use this short trick. So that's the answer for what? Question 5. This is question what? Question 6. This question 6, the half-life of radioactive substance is 14 days. If the 48 grams of the substance is stored, after how many days will be 1.5 gram of original substance will what? Will remain. So in this one, we are given what? The initial to be 48 and the final of atom will be what? Original one will be initial is 48. The one that is remaining is what? 1.5. You are now asked to find the what? The time, which is what? Capital letter what? Capital letter T. So, capital letter T. If that be the case, question number what? 6, you can now say what? The distribution what? Ratio R. No, we can say what? N, given that our N, or even N naught is 40 what? 8 what? 8 gram given, and the normal N is what? Is 1 point what? 5 gram. The one that is removed is just and the half-life is 14 days. Good. Capital letter T, half-life is what? 14 days. We are now asked to find the what? The small what? The T. If you are given this kind of what? Of question, the last formula I gave you under kinetics of radio what? Activities. Which formula says that what? Using that we have capital letter T should be equal to T over what? Logarithm of R into base 2. Where this R is what? Where R is distribution ratio, which is N naught over what? Over N. What is N naught here? R 40 what? 48. This 0.5. Divide this divided by what? 48 to give us what? 32. That is what? For our what? Our R. By substituting for it, abi, our R is 32, our T here is 14. Substitute for them, we have 14. Small t is unknown. Logarithm of what? Of 32 to base 10. By cross the multiplication, this t will be equal to the what? 14 multiplied by logarithm of what? Of 3 to what? To base 2. If we solve it in logarithm, logarithm of 32 base 2 will give us 5 times 14. We have what? 14 multiplied by what? 5. Finally, our what? 14 times 5 it will give us 70. We have 70 what? Days. Therefore, define the t there is what? 70 days. That should be the what? The final answer for question number what? Number 6. And the question number 7, you are asked to find the count rate of an alpha particle source of 400 per minute if the half-life of the source is 4 days. What will be the count rate per minute after 15 days? Count rate per minute after 15 what? 15 days. We are given what? Small t should be 15. The half-life should be 5. For you use this 2 to find the what? The n. If we use 2 to find the n, yes, we can use the n to find the what? Our. Okay, good. Let's solve it. Question 7. Our n naught from the question particle is 400. For what? 100 per what? Per minute. What is the next one? If the half-life of the source is this, okay, and the n is what? Unknown. The small letter t from the question we are given to be what? Small letter t is 15 days, abi, and the half-life, the small letter t is 15, half-life is 5, and the capital letter T, which is half-life, is what? Is 5 what? 5 days. So we are now asked to find the what? The n. So it's very easy. We will apply this formula using the integration ratio should be 2n. Where what? This is the integration ratio we know before. This is what? R is always what? N naught over n should be equal to the what? 2. This n is small letter n t over what? Capital letter what? T. So by apply this now, I think we get our answer. So what is what? Our n. We have 400 count rates over what? Over n. Then we have 2 here. So what do we have? 15 divided by 5. We have 15 divided by what? 5. We have 400 over n. 2 here is 3. So this will be what? 400n is equal to what? 8. By doing that, we will have our what? N should be equal to what? 400 divided by what? Divided by 8. 4 divided by 8, Abi 8 divided by 400, we have what? 50 per minute. That's what? The count rate per minute after 15 what? 15 days. Just try to familiarize yourself with what, how to use what, all these short formula. So it's remaining 4 questions. So let me rub it up and solve it. So let's solve the question what? Number 8. In 90 seconds, the mass of radioactive elements reduced to 1 over 13. Good. Of its original value. Determine the half-life. So we are given what? T should be what? 90 seconds. And we are also given what? The distribution ratio should be what? 1 over what? 13 of original what? Value. Abi? You can now say that what? We call that functional remaining equal to what? 1 over what? Half. That will be functional what? Remaining. This statement, it will be the same as what? We have 1 over. From the same that we have what? 1 over what? 13 equal to the what? 1 over what? Half. From this expression, you can have what? Our half should be what? 13. Good. So we are looking for what? Capital letter what? T. We are looking for what? Half-life T. Abi, using that half-life T is equal to the what? T logarithm of R base 2. Remember this short trick that I gave you that time? Applying this, we know this one as this. We have known our R. By putting it there, the T will be equal to the what? 90 into what? Logarithm of what? Of 13 into base what? Base 2. Abi? Yeah. So, yeah, you can. There's a little mistake here. The radioactive element reduced to 1 over 32 is not 1 over 13. Sorry. Here it's supposed to be what? 1 over what? 32. So R will be what? 32. So since this is equal to the what? 32. Yes. You can write it in this form. 90 over what? Logarithm of 2 raised to the power 5, give it 32 to base 2. It will come to the front. You now have T should be what? 90 into 5 into logarithm of 2 to base 2. Log 2 base 2 is 1. You have 90 over what? Over 5. At the end of the day, it will give us what? 40. How many 5 we have in 90? That will be 18. We have 18 what? Seconds. So that is what? Half-life of minutes. So the next one is question what? Number 9. So the number 9 question, we are given that a sample of radioactive elements. The question number 9, we are asked what? A sample of radioactive sample substance was found to be left with 132. That means what? Fractional this is 132 of its original count rate after 100 what? Years of original count rate after 100 what? Years. So my T is what? 110 years. Good. Calculate its decaying what? Constant. So the lambda is what? Unknown. So to know the decay constant here, we will apply this formula using lambda should be equal to the what? 2.303 logarithm of r, logarithm of r over what? Small t. Please note this formula. And we all know that what? My this thing is what am I call this thing, Jerry? The FR, fraction remaining, fraction remaining is what? 1 over half, which is what? Same thing as what? 1 over what? Can I say that 1 over 3 2 equal to 1 over half. Therefore, R is what? 3 what? 3 2. Have you now? So if you substitute for what? For the value, lambda we have 2.303 logarithm of what? R, which is what? 3 2 over what? Time, which is 110. By the long process, pressing all the calculator, you must arrive to the 0.0315 per what? Per seconds. That's the answer for that one. Let me solve the 10 questions. You help me to solve the what? The 11, and put your answer in the comment section. 10 and 11, they are what? They are the same. A radioactive sample initially contains n atom after 3 half what? 3 half-life, the number of atoms. Yes, here we are given what? Question number 10. We are given our n should be what? 3. So if you are given n should be 3, we know that what? R is equal to the what? 2 raised to the power n. Therefore, we can have our R to be what? Raised to the power 3. Our R is what? 8. Is the ratio what? Ratio. Good. We are asked what? After 3, this number of atoms. The number of atoms that it is great is, and the number of atoms that is great after taking half of life fraction of this material and decay. This question 10 and what? This, they are almost what? The what? The same. If you ask such this, apply this formula to solve it. Decay, it will be the initial one into R minus 1 over what? R. If I apply this formula, I think we can get our what? Our answer. So this n, we mean n naught will be R is what? 8 minus 1 over what? Over 8. It will give you what? N d, what is the what? N naught. This ratio will be what? 7 over what? Over 8. That will be the what? Answer. Therefore, ND will be 7, 8 remaining over 1 over 8. That's the final answer. You can solve the word for 11 questions and put the answer on the comment section. And the last aspect of radioactive activity or nuclear chemistry we are going to treat is the binding energy and the mass what? Defect with our own calculation. So in the next video, don't forget to like, comment, and subscribe. Thanks for watching.